Shalom to everyone. I see that we have over 400 participants. This is wonderful. Welcome to the Bekenstein Lecture in Fundamental Physics 2022. And it's really good to see or have all of you. Let me start by inviting Eran Sharon, head of the Racah Institute of Physics, to welcome us.
Dear Bekenstein family, dear Professor Penrose, dear colleagues, welcome to the sixth Bekenstein Memorial Lecture of the Racah Institute. This lecture, together with the Racah Lecture, is one of the two main annual events of our institute, in which we memorize great colleagues of ours by hearing, by inviting key speakers and hear from them new and exciting and pieces of physics. I will not take more of our time, since reading the abstract of today's lecture, I'm already excited and curious to hear the talk. So I will give back the speech to Barak Kol, who is the head of the Bekenstein Lectures Committee. And Barak will lead this event. Welcome, everybody.
Thank you very much, Eran. So this year, in addition to the audience from the Racah Institute of Physics and other departments at the Hebrew University, we also have participants from throughout Israel as part of the Israel Physics Colloquium. Before I introduce our special speaker, I would like to tell you a bit about Jacob Bekenstein, and especially to tell those who did not know him in person. Dear Bekenstein family, dear participants, our distinguished colleague, Professor Jacob Bekenstein, is known throughout the world as the discoverer of black hole entropy and for several other achievements. I believe that black hole entropy would be discussed during the talk, so I would not explain it any further. Bekenstein's scientific achievements were recognized by numerous awards, including the Israel Prize of 2005, the Wolf Prize of 2012, and the Einstein Prize of the American Physical Society in 2015. Sadly, he passed away unexpectedly in August 2015. To his memory, to the memory of this great Israeli scientist, our institute established a yearly lecture in fundamental physics, as mentioned already. So Jacob was born in 1947 in Mexico City. His parents were Jewish immigrants from Poland who met in Mexico during the war. In his youth, his family moved to the United States, first to Texas and then to New York. He attended the Polytechnic Institute of Brooklyn, where he received a master's degree in 1969. Then he attended Princeton University, and it was there that he discovered black hole entropy in order to answer a question by John Wheeler, his thesis advisor. He obtained his PhD in 1972. After a two-year postdoc at the University of Texas at Austin, he accepted a faculty position at the Ben-Gurion University, of course in Israel, and moved to Israel. Finally, in 1990, he moved here to the Hebrew University of Jerusalem. Bekenstein has written a charming and witty scientific autobiography titled, let's see if you can see it, maybe it's mirrored, titled titled Of Gravity, Black Holes, and Information. And out of it, I would like to read to you a few quotes in his own words. First, I was joyed to stumble over a few mentions of our speaker today. In the part regarding his graduate studies in Princeton, he writes, black hole physics, as we understand it today, started then in Princeton, and more or less simultaneously in Moscow, where the group of Yakov Zeldovich and of Vitaly Ginzburg worked, and in Cambridge, in the collaboration of Roger Penrose with Stephen Hawking. In another place during his graduate studies, he writes, in Princeton, we used to hear all the news about the current developments in gravity. not just from local people, but also from visitors. And then immediately, first visitor, thus Roger Penrose came to visit us a couple of times. Now to several lessons about physics that Jacob suggests to us. And for that, we return to his college days. So he says, about the challenge of physics, he writes, it took me a long time to get the concept right. He refers to Green's function, and I came close to despair at times. I learned then that physics does not come easy. The concepts are far from everyday life and tax the imagination. Only hard work and perseverance can break down barriers. He also talks about failure. I particularly recall getting a very low grade in a chemistry quiz. Although all students were in the same boat, I had a record of excellent grades in high school and took that failure very much at heart. I quickly drew conclusions as to how to study from then on. This little crisis was a good example of how a failure due to a misconception about a subject can serve as a tool for changing oneself for the better. I have experienced quite a few of these blessed disasters in my life. And finally, on the success, after failure, on the success of a college project. It is hard to convey the elation one feels upon perceiving a new idea, particularly one which is sufficiently elaborate that it would not occur to most people. You just have to experience it. I am sure he felt this way when he discovered black hole entropy, the Bekenstein bound on entropy, the relativistic theory for Mond, and much more. Now, let me turn to our special speaker today, Roger Penrose from the University of Oxford. Simply put, Penrose is one of the founding fathers of black hole science and more generally of contemporary general relativity, namely relativistic gravity. He demonstrated the necessity for singularities to exist within black holes, and on the way defined marginally trapped surfaces, which are related to horizons, the defining properties of black holes. General relativity is notoriously hard to visualize, as it requires to come to terms with a four-dimensional space-time. Through his geometric insight, Penrose enabled us to see, to visualize such space-times, and he introduced the so-called Penrose diagrams. Today, everybody who does GR uses these diagrams. I will not go through the long list of his other inventions. I will just mention some: cosmic censorship, twistors, another geometric tool, the Penrose process, and outside of general relativity, related to tilings of various things, including floors, the Penrose tilings. His achievements were recognized by numerous prizes, including the Wolf Prize in 1988, together with Stephen Hawking, the Nobel Prize in 2020, namely last year, together with Gensel and Guess. In addition, he was knighted in 1994 and added to the Order of Merit in 2000. That's a highly selective cultural order of the United Kingdom and the Commonwealth. I will end with a couple of anecdotes. Naturally, we in Israel are interested in aspects relating to the Jewish people, so I can mention that some of the speaker's ancestors were Jewish. Also, I can mention that in the last summer, I think it's not a secret that he celebrated his 90th birthday. So warm congratulations. And please join me with a warm virtual welcome to Professor Roger Penrose.
Do you want me to start?
Please.
Oh, okay. Well, thank you very much for the introduction. It's certainly a great honor for me to be able to pay my respects to Jacob Bekenstein mainly for his magnificent introduction of the idea of the black hole entropy. It was somewhat refined by Stephen Hawking, so we sometimes call it the Bekenstein-Hawking entropy, but Bekenstein had the basic idea, and the discovery by Hawking of the exact formula for, well, the coefficients in front of the formula that Bekenstein introduced. Well, it's not very important for what I want to say. The main thing is that black holes have an entropy which is in proportion to the surface area of the black hole's horizon, which is a very simple idea and a very powerful idea. More than that, the entropy in the universe today is completely dominated by the Bekenstein entropy. So when we think of entropy, well, entropy basically means the randomness in the universe. And we have the second law of thermodynamics, which asserts that this randomness increases with time. And the Bekenstein entropy is what dominates the entropy in the current universe by a huge factor. This is because we, as time has progressed, we have discovered, when I say we, astronomers have discovered the black holes in the universe, bigger and bigger ones, and the big ones really dominate this entropy completely. So when we talk about entropy, if we want the whole entropy in the universe, we're really talking about the Bekenstein entropy. Now, let me explain a little bit more, a very simple idea, which is at the basis of what I'm talking about. Here I have some pictures. I'll come back to this picture later on, but it's an important one to get the idea. The top three pictures, going from left to right, represent a gas in a box.
You are not in display mode.
Can you not see my picture?
That's fine. We shall continue in this way. Please proceed.
This is the way we agreed to do it, I think, so I hope it works.
Yes,
I hope you can see my picture. The fact that you can see the other pictures at the side, you should blank those out from your mind. The main point is the big picture in the middle, which I hope you can see me circling. Okay, now this big picture has 3 at the top, 3 at the bottom. Time is going from left to right. Entropy is also increasing from left to right. And at the top 3 pictures, we have a gas in a box. And I want to imagine that we start that gas off in a much smaller box in the bottom left-hand corner, bottom right-hand corner, sorry, where we imagine the gas is trapped. We then open that box and the gas starts to spread out through the box. The distribution becomes more and more uniform as time progresses. And this is a normal thing. You imagine as entropy increases, things get more random. And in ordinary materials, this is the sort of picture. They just spread out and become more and more uniformly distributed. Certainly with a gas, that's the sort of thing we expect. Now, the bottom 3 pictures show us the analogous thing with gravity. So I'm imagining not now molecules of a gas, but stars, which could be simply roaming around, maybe in a galaxy. And the first picture on the left-hand side at the bottom, we see a distribution of stars, fairly randomly distributed. And as time progresses, they tend to clump through the action of gravity. They clump more and more and more until over at the right, we also see that there's a black hole where the entropy goes shooting up. Now you see that entropy is going up with the increasing irregularity when it comes to gravity, as opposed to normal materials when entropy goes up is accompanied by more and more uniformity. This is a point I want you to keep in mind because it is central to a lot of things I want to say. So let's move forwards now and talk about the theorem which I produced in 1964, published in 1965, and which seems eventually to have won me a Nobel Prize. This theorem was to show that you have a distribution of matter which gets too clumped together. There may well be no escape from it becoming singular. See, there was a paper published by Oppenheimer and Snyder just before the war, 1939, I think. And this showed that if you had a dust cloud, this meant a cloud of material which was technically called dust. That means there's no pressure in it. And if it was spherically symmetrical and was sort of too big, it would collapse inwards. And since there's no pressure and it's exactly spherically symmetrical, everything falls towards the center. And it's not so surprising that what you find in this situation, that the density becomes infinite in the center. And this was the picture that Oppenheimer and Snyder came to. Now, lots of people, it actually was a model of a collapse to a black hole, but many people were very skeptical of this for two reasons. One was you didn't have any pressure in the material, so there's nothing to stop it. The more important thing is that it's assumed to be exactly spherically symmetrical. So everything falls in towards the center. There's nothing to stop it. The density will go up and sort of become infinite for this fortuitous fact that it's focused into this central point, and nothing can stop it. Now, this was, I think, the normal view that people had, that if you had a more complicated situation with irregularities, that it would swish around and come swirling back out again. Now, this was the sort of picture that people began to worry about in the early 1960s, when quasars had been discovered. These were radio signals which showed that there were signals which seemed to be very strong, coming from some event which must be very, very far away, because it was redshifted. That means partaking of the expansion of the universe, and so frequencies were moved over to the red, and this was the belief that this was redshifted, and therefore it was so far away because of the redshift that there must be an enormous amount of energy coming out of it. And also because the intensity of this energy varied within weeks and so on, like not very long. This suggested that they couldn't be very big, and no bigger than the solar system. And this suggested to people that you're looking at something which was comparable with the kind of radius that you get into trouble, which is called the Schwarzschild radius. And I have that in the picture here. This picture is a picture from my paper, and it shows time is going upwards in the picture. You have to imagine another dimension, because I can't draw all four of them. I can only draw two, actually, because it's on the plane, but you have to visualize two spatial dimensions and one time dimension going up the picture. And what we have here is a symmetrical distribution of material which collapses inwards until it reaches this radius represented by that cylinder that you can see. That cylinder at the top represents the Schwarzschild radius, which is a radius at which, according to the Schwarzschild solution, Schwarzschild introduced this spherically symmetrical solution of the Einstein equations very soon after Einstein had introduced his theory. And it's the one we tend to use if we're looking at spherical symmetry. So with spherical symmetry, you have this well-defined horizon, and when the material falls within it, well, people used to think it was a singularity, because in the initial coordinates that Schwarzschild introduced, it looked as though everything went crazy at this point, that horizon. But then we discover it's not a singularity, it's really a horizon, and the material can fall through it. So that was the picture of the Oppenheimer-Snyder collapse. But what I was imagining is, suppose you have the collapse in the sense that the material has qualitatively looks like this, but not exactly like this. It's got irregularities, and you have this little thing that looks like a ring going around it. This ring is what I call a trapped surface. It looks like a ring, but you have to imagine again that there's an extra spatial dimension. So it's really got the topology of a sphere, not a circle. So you have to think of that ring as really a sphere. And I'm imagining a flash of light taking place on that sphere. And you would imagine that the outside flash of light would go outwards and the inside would go inwards. But what you find is when it gets inside this Schwarzschild radius region, then the outward flash is also going inwards in the sense that the flash is reducing in its area. And this is what I call a trapped surface. And if you wiggle it, you say it's not a feature of spherical symmetry. You can imagine perturbing it and having it quite irregular, but still having this property that the outward flash is sort of focused inwards too. And then I was able to show that if that happened, there was no way of avoiding a singularity if you assumed that space-time didn't stop or something like that, or that space-time didn't go singular. Well, if you assume it doesn't go singular, what happens? Well, that's the question, you see. If energy doesn't go negative, can you avoid it going singular? That was really the question. And what I was able to show using arguments, well, let me show some of the other pictures. I think I have to put on them down here. Most of the pictures I will show depend on the light cones. Here we have the idea of a light cone, or a null cone, I should call it. It's a local structure. here we have in the middle a point in space-time, and here we have the light, a photon. This is the, if you imagine a photon as a particle traveling with the speed of light, the cone itself is generated by these light-like lines. So the history of a photon, it travels at the speed of light. So you have to have you imagine that your time coordinates and your space coordinates are such that the speed of light is more or less tilted with so that you have to have your units so that the time and space units are comparable, in the sense that if your spatial units say a light second or something, then your time unit is a second. If your time unit is a year, the space unit is a light year, something like that, so that your pictures look reasonable, other than this light cone being completely squashed on the plane. So if you use units like that, so the speed of light is something you can draw a picture of, then this is the idea, and you would have one time direction and 3 space directions. You can't really draw all those at once, so you have to imagine there's an extra dimension to give you the full dimensionality of the cone, which rather than being 2-dimensional would actually be 3-dimensional. Okay, so that's the light cone, or the null cone. At each point in space-time, you would have one of these cones. So again, you have to imagine there's another dimension there, but nevertheless, it could be very irregularly distributed over the space-time, not necessarily in any sense pointing upwards, whatever that means. They're distributed in a way like this. Okay, so that's the general picture. And if you're thinking about the world line of a particle, so that world line means the history of a particle, it would always be within the cones. So the direction of the vector tangent to the curve representing the history of that particle would always be within the cone. If it's a photon, it will be always along the cone. So this is the difference. Matter particles, the world lines are within the cones, and light rays are along the cones. So that's the sort of thing you have to get used to. And this is the important sort of idea. When I talk about a little cone like this, I should really call this null cone, to distinguish it between the light cone. That is the actual structure. Starting from a point in space-time, you look at all the light rays coming out of that point. These are the null GeoD6, these are the straight lines, if you like, as straight as they can be, which are along the cone. So these are the paths of light rays, and that is the light cone of that point in the center. Now, the thing that at the back, you see, it can start doing awkward things like crossing over itself. And in the picture, I'll show you that what these sort of awkward things look like. This is what you've got to face up to, is that the boundaries of light cones can be complicated things, and it's to see what's going on, it really gets very involved because of these caustics and crossing surfaces. And the nice thing that I realized is that if you stop them off where they start to cross, in other words, you look at the boundary of the future, you can forget about all these complicated stuff in the middle, and they stop off and produce a nice surface. I won't go into the details of how the theorem worked, but I just wanted to say that you could use the ideas that I've just been talking about to show, and let me go back to the picture I had previously, this picture here, you could show that the future of this so-called trapped surface, which have this factor, that property that the light rays start to converge, the future of that trapped surface is something where the light rays start to converge, then there's no way of stopping them coming together, and the future of that has to be what's called a compact region, and then you tie this in with a non-compact region of the initial surface that's produced this collapse, and you get a contradiction which shows something goes wrong. Something goes wrong really means that your light rays somehow stop. How can they stop? Well, they stop because they run into some horrible thing, the singularity, which means for some reason or other, the space-time stops. One normally assumes that the reason, and I didn't say this very explicitly in my paper, but one normally assumes that what happens is that the space-time curvature gets so big that one cannot avoid bringing in quantum mechanics. You have to bring in quantum gravity. I want to come back to this a bit later on because it's an important feature of what I want to say. But this is what people would normally say. It's the view I had at the time, and it's certainly the view that Stephen Hawking happened when he picked up on this in a way which I'll describe in just a moment. This was what you have to expect, that when you get too much material collapsing together in some region, that it will lead to these singularities where presumably the classical physics, which I'm talking about, where the energies, the local energies become, well, what happens? Do they become negative? That's one thing that might get rid of this problem. Or do you simply get curvatures which get worse and worse and worse, and they simply have radius of curvature so small that you have to worry about what's called the Planck length. I should say the Planck length is where you bring quantum mechanics and general relativity together, and you see that the length is what's called, well, it's 10 to the minus 50, well, it's about 100, it's several orders of magnitude smaller than a radius of a proton. You have to look at, I think, 20 orders of magnitude. So you're really looking at ridiculously tiny, 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 tiny scales, much smaller than the ordinary kind of scales we're talking about in particle physics. So only at that scale do you start to think that quantum gravity comes in. But that's what people were talking about. Okay, well, let's move on and see where we go from here. Where we go from here is I want to talk about, well, that's not this. This is a key thing that I wanted to involve in the discussion, is here we have two kinds of curvature. Now, I'm imagining here you are at a point looking back along your past cone now. So that's the light rays coming into your eye. And some of these light rays will start getting focused like being with a positive lens. If you imagine there was a positive lens focusing inwards the light rays, this is what happens with matter. Ordinary matter behaves like a positively inward focusing lens. But if you have astigmatism, it squashes as much in one direction as it stretches in the other direction. This is what's called the Weyl curvature. Now, the Weyl curvature is the conformal curvature. I'll come back to that later. The Ricci curvature is what, according to Einstein, is what matter produces. So if you have matter, this causes this inward focusing. And in the next picture, I'll show you the sort of thing which was really a very, the original thing which confirmed Einstein's theory when the expedition, Eddington's expedition to the island of Principe, and during the eclipse of the sun by the moon, you could actually see the stars, and the stars were displaced outwards, which really, you see, you must imagine that the sun itself acts like a positive lens because there's a lot of matter in the sun. So this is the inward focusing due to the matter in the sun. And since it's a positive lens, it needs to expand the image behind it. So it behaves like an ordinary magnifying glass. So the image behind it gets expanded, pushed outwards. So that means that the image outside the sun gets pushed outwards too. When you push it outwards, the outward pushing gets less and less as you go outwards. So this leads to a distortion. So you can see an initial pattern which might look like circular if the sun wasn't there. And if the sun is there, it gets pushed outwards and that circular pattern looks elliptical. So this change of the circular feature to an elliptical one is the effect of the Weyl curvature. So that's the sun's gravitational field, which is causing this distortion effect. The Weyl, that's the curvature due to Hermann Weyl. That's when I say the Weyl curvature. It's the part of the curvature of space-time which is not due to matter. You subtract out the part due to the matter, and this is the part due to pure gravity. So the important thing is to realize it's this Weyl curvature which measures the distorting part, which measures the gravitational field directly, not the effect of the matter, but the free gravitational field outside the sun, not the matter which is causing the positive focusing, the magnification effect, but the distortion effect, which is due to the Weyl curvature. Okay, well, that's the general picture. And it was this picture that I certainly had in producing the singularity theorem. And the fact is that the Ricci curvature causes positive curvature, and the Weyl curvature doesn't initially cause positive curvature, but if you have a lot of it jiggling around and doing all sorts of things, there's an initial net effect, which is also positive, which is in effect the energy due to the gravitational field. Okay, well, let's move on to the next picture. You see, I gave a talk in Cambridge. I gave a talk in London about this theorem I had in 1964. I think it was December 1964. I remember being very proud because the great Irish geometer, J.L. Singh was at my talk, and I was very pleased he was there. According to the movie, Stephen Hawking was at my talk, but this is completely false. He was not there. But J.L. Singh was there, and I was pleased that he could witness this discussion of the singularity result. There was a repeat of my talk. Dennis Sharma invited me to give a repeat of the talk in Cambridge, where Stephen Hawking was present. And we had a long discussion afterwards with Stephen and George Ellis. And we talked about the methods that I was using to prove the theorem in the black hole singularity theorem. And Stephen then picked up very quickly on these ideas and generalized them and applied them to the Big Bang. So here we have a picture now, a cartoon of the Big Bang, where the bottom of you see the time is going upwards. Time tends to be going upwards in my pictures. I have to suppress a couple of dimensions, never mind about that. But we have the singularity of the Big Bang in the normal cosmological models. We also have this exponential expansion that's starting in the remote future. This is due to the cosmological constant, or what people call dark energy. I don't like the idea, the term dark energy, because it's not energy, it's not dark. You see through it, it's invisible rather than being dark. It's not really energy because it pushes rather than pulls. It goes the wrong way around for energy. So it's really rather a confusing term. But nevertheless, Einstein introduced this term for the wrong reason, unfortunately, because he wanted to have a static universe. He retracted it because when he realized the universe was not static and expanded. Nevertheless, he'd already introduced the idea, and it was too late to retract it, just as well, because it turned out to be right. Even Einstein's mistakes sometimes turned out to be right, as in this case. So we did have this effect of the term that Einstein put in, or something else. It might be something else. People often more open-minded than I am, and they call it some mysterious dark energy. I like to call it the Einstein cosmological constant, which seems to be a perfectly consistent explanation of why we have this exponential expansion as time goes on. I have not tried to prejudice the idea as to whether the universe is spatially closed, so it goes round and round spatially, or whether it might go on. As you see at the back, I put in this wiggly possibility that it might just keep on going. Whether or not it does is not part of my discussion. It might continue, may be closed up, or it might not. It doesn't matter to what I want to say later. It did matter for the Hawking theorems, and there's lots of discussion whether it closed up or not. And we got together after he proved several theorems, very beautiful generalizations of what I'd done, introducing new techniques that he'd introduced, and was able to show that if you perturb the black hole singularity, you will still not avoid having the singular initial state. So that was generalizing my arguments to the case of the Big Bang. Now, I want to introduce a concept which is common nowadays. If you look very closely at the Big Bang, and here I've got this sort of magnifying glass, you have to have a very, very powerful magnifying glass, much more powerful than this one would be, but never mind. What you actually see, according to current theory, well, you see another exponential expansion. This is what's called inflation, and current cosmology believes that this is a significant part of the early universe. It doesn't really matter much to what I want to say. I have to say that I was always very skeptical about inflation. Recent discussions I've been having with Krzysztof Meissner in Poland, where we have some nice results, which we're working on at the moment, show that perhaps there was an inflation of some sort. I don't want to go into that here. There are very interesting questions raised by this. Whether there was an inflationary phase or not doesn't really make any difference to the overall discussion. The point I want to say is that whether or not there was inflation, and I was always very skeptical about this, certainly in the kind of inflation that people tend to argue for in the current cosmology, which would be a very dramatic thing. But nevertheless, whether that happens or not, if we imagine reversing the time, and that's what I want to picture here. If you go back to my earlier picture and reverse, that was the picture here before the magnifying glass, here we go. If we imagine the universe collapsing, but let's put irregularities in. So let's put a little bit of wiggles in this space. These wiggles will tend to grow and grow and grow and get more and more complicated whether or not inflation is there. In fact, the kind of situation we have here is nothing like what you need for inflation to work. It just doesn't even work in this situation. What you would get generically is some horrible mess where the Weyl curvature dominates. I should explain that there was an interesting feature in all this, that before I proved my result, the result I mentioned, that won the Nobel Prize apparently eventually, there was a paper by two Russians, Lifshitz and Khalatnikov, which seemed to have proved that in the general situation, you would not get singularities like this. The thing would sort of collapse around and bounce out again. So that was the view they had. There was actually a mistake in the paper. I had a look at the paper. I didn't see the mistake, but I was a little bit doubtful whether you could prove something general like this by those means. And so I looked in my own way at the problem and came to the opposite conclusion, that singularities had to be generic. I should explain that after my paper came out, the Russians took it seriously and Belinsky got involved together with Lifshitz and Khalatnikov and proved a more powerful result, a more correct result, because they corrected the mistake and found that this was in fact the generic situation, that you get very, very complicated behavior where the Weyl curvature goes completely wild and dominates the situation. So now the argument is that this is really what you must expect. Something like this. If you have irregularities, they will build up, get more and more complicated like this, whether or not it's not even a situation you could have inflation. It's not the kind of background in which inflation could work. So it's just not clear to me how you can avoid having this. And this is the picture that we're presented with. Okay, if we're presented with that as the generic thing in the future, why didn't we have this as the generic situation in the past? There's absolutely no reason why you shouldn't. It's a huge assumption that that is not what happened. Why you get this rather than that? Well, you can make one theory or another, and people do have different theories, and different theories sometimes that it actually collapsed in some way which had symmetry and then bounced. But then there's a lot of assumptions in that, which is why you don't get the generic situation. And I just don't see why quantum gravity or whatever. I used to worry about quantum gravity. Maybe quantum gravity is some completely asymmetrical theory. What you have to explain is really this. You see, when you think about the Weyl curvature, what it says, what I'm trying to say is that we seem to see, and this is just from what we see of our universe, without much in the way of theory, but when I talk about the future, it's what we seem to expect. If we had a collapsing universe, we would expect the Weyl curvature to dominate and become completely wild, go to infinity, and for the past, it goes to zero. So this is what we seem to have with our universe, with the second law of thermodynamics, agreeing with the Bekenstein type of formula where the entropy goes up and up into the black holes. And how do you get it back out of the black holes? It's very unclear. It will be in there, it will dominate, and the Weyl curvature will become infinite. You have to worry about the evaporation. I'll come to that later, of the black holes. It doesn't solve this problem, but let me leave that for the moment and come back later to it. But we still have this problem of why it is that the Weyl curvature goes to zero for past singularities and goes to infinity in the future ones. I used to think that, okay, it's quantum gravity, but it must be a very, very peculiar kind of quantum gravity, which for some reason it says that the Weyl curvature goes to zero at the beginning. So that was the idea I had. Let me talk a bit about this picture, because here I have this is the Kobe satellite, the first satellite that went up to look at the universe. There's the Planck and the WMAP satellites afterwards, in the other order actually. But the Planck one was the first one, and this was this incredible observation of the microwave background. This microwave background, which seems to have been released from the very early universe 380,000 years after the Big Bang. That's when the universe cooled down enough that radiation could finally escape and get out, and that's what we see, is this microwave radiation. It was discovered by Penzias and Wilson, and they saw this incredible radiation, which is such an important feature of current cosmology. But the main thing that they observed is this curve. This curve is, well, the actual observations are represented by this curve. The curve is actually the Planck curve, which represents you see what we've got is the horizontal axis is the frequency, and the vertical axis is the intensity. So for different frequencies in the radiation, you see this particular curve. What does that tell us? Well, first of all, the thick line is the Planck curve, which tells you what you're looking at is thermal equilibrium. You're looking at that was the origin of quantum mechanics. In fact, this curve was like that if you have a gas in a box, and you wait for it to get into thermal equilibrium, maximum entropy state, into its maximum entropy state, then you find the frequency and the intensity has this very, very distinctive shape. And this is what we see. What you see are the error bars for the actual observations, but you have to bear in mind that these error bars are magnified by a factor of 500. So they're really 500 times shorter. So even the worst ones right over down at the right-hand side still hug the line. So the thickness of the incline is far, far fatter than the errors in the observations. So what you're seeing in this radiation is a very, very, very close thermal equilibrium. So you are seeing, like the gas in the box, which I think I repeat in my next picture, if it's that one. Yeah, here we have. What you're seeing is something like the top right-hand picture. You're looking at matter and radiation in maximum entropy state. Now, this seems to me a very great puzzle, maximum entropy state. Because what does that mean? Think about the current universe. This is now a long time ago. This is 380,000 years after the Big Bang. This is very, very early in the universe. So you're going back and back and back and back. And what is the earliest thing we see? Thermal equilibrium, maximum entropy. Now, the second law of thermodynamics says that the entropy goes up. It doesn't come down. So when you go back and back and back, you ought to see low entropy so that it can go up in order to reach our current state. You might worry about the universe being expanding and all that. That actually is a bit of a red herring, because you can think about it. It doesn't mean there's any more room for entropy as the universe gets bigger. That's not the explanation. It's nothing to do with the universe expanding. You are looking at something where the entropy is very, very large in the gas in the universe. But it's not large altogether because of the bottom three pictures. Because the gas in the box, if we're just looking at ordinary matter, if we're looking at ordinary stuff in the universe, not gravity, but everything else, yes, indeed, that would represent the maximum entropy state. It would have nowhere to go. We would already still be in that maximum entropy state. We wouldn't be here. We would just be a gas. It wouldn't be interesting at all. But what's happening is that the gravity starts to take over. Eventually, it starts to take over and it wins. The entropy becomes in the black holes, it becomes in the entropy, Bekenstein entropy, it becomes in the black holes, and it goes up and up because there's an enormous amount of room for a lot more entropy in the clumping together of the material. So we don't see maximum entropy. We see maximum entropy in the material, minimum entropy in gravity. So the puzzle, this seemed to be the huge puzzle, that why is it that the universe was somehow singled out to be very, very maximally entropized, if you like, maximally thermalized in the matter, but the universe had its low entropy all the time hiding there in the low entropy in the Big Bang. So the Big Bang was very special in this particular way. It's something which applies to the Big Bang. It can't just be ordinary quantum gravity, because quantum gravity is not asymmetrical in time. So I said, well, we've got to look for something asymmetrical in time. Now here, let me briefly talk about something which is I think the route that I was taking for a long time, because I thought when we try to bring quantum mechanics and general relativity together, do we have an ordinary quantum mechanics or do we have a funny quantum mechanics in some way? And I want to try and explain that I believe we must have had a funny quantum mechanics in some sense. What do I mean by a funny quantum mechanics? Well, I want to say that I'm trying to bring together the two basic principles, one of quantum mechanics and the other of general relativity. What's the basic principle of general relativity? The principle of equivalence. So the top picture here, we imagine Galileo or somebody, theoretical Galileo, dropping a big rock and a little rock from the leaning tower of Pisa. And according to what Galileo said, the big rock and the little rock would fall together. Of course, he understood air resistance would make a difference. He said, well, suppose there was no air resistance. He understood that perfectly. Then an insect looking on the big rock, looking at the little rock, would see the two as though there was no gravity. As long as it falls, you can cancel gravity out by falling freely. At the bottom, I have this futuristic 2001 type space center. And here we have an astronaut floating freely, even though the Earth is here, somehow falling freely, as long as you're looking at the biocurvature and details like that, falling freely, you can cancel out gravity. And this is this feature that the gravity has no other force of nature has. It's a very special feature of gravity. Now here in this picture, I have an argument. I'm not going to go into this here, but it's an argument I produced quite a long time ago, that if you try to do quantum mechanics and you want to take the Einsteinian view seriously, or the Galilei-Einsteinian view, if you like, that you can get rid of gravity by falling freely with it. Now I'm trying to imagine doing an experiment on a tabletop, and I'm not actually doing the experiment, but just talking about it theoretically, that the experiment involves the taking into consideration the Earth's gravitational field. Now, the Earth's gravitational field, you could treat just like an ordinary force, that would be the Newtonian way, if you like, or you could treat it as something which you can get rid of by falling freely. That's the Einsteinian view, that's the Galilei-Einsteinian view, that if you use coordinates which fall freely, then there is no gravitational field. You simply do your calculation, and what you find is that the Newtonian view and the Einsteinian view, one of them is the green and the other is the purple, that they actually are more or less the same, rather miraculously. You find it comes out to the same, apart from what's called a phase factor. So you have this phase, this is this multiplying factor, which according to quantum mechanics, you say, well, you can ignore this phase. Then you look carefully at it, you say, oops, you can't really ignore it because it involves the time in a curious way. There's the time cubed in there. What it means is that the 2 points of view belong to what's called in quantum mechanics, two different vacua. So you have two different quantum field theories. Then you can say, who cares which quantum field theory you work, as long as you stick to your quantum field theory. That's true, but suppose you change your experiment a little bit by saying that there is a body in this, so this is this blue and purple brown version of the body. So it's put into a superposition. This is the principle of quantum mechanics, that you can put things into a superposition of two different locations. That's a fundamental principle. If it could be here, and if it could be here, then you can have states where it's here and here at the same time. If that could happen, then you have to superpose their gravitational fields. Then you have to superpose their vacua, and that leads you into a contradiction. To get rid of the contradiction, you try to, well, what you find is it really gives you a measure of error, an uncertainty in the energy, and then you use Heisenberg time uncertainty to say that there's a lifetime for this state. I don't want to go into the details, but I'm saying, looking at these two fundamental principles of Einstein, Galileo, if you like, Einstein, and the principle of quantum mechanics, of the superposition principle, you find they're in conflict. And the conflict can be resolved by saying there is an energy uncertainty in the superposition, and then you use Heisenberg time energy uncertainty to give you a lifetime for this state. So this is well, Dioschi had come up earlier with the same sort of conclusion, that the idea is if you have a state with a superposition like this, then there is an uncertainty in it, and it gives you a lifetime of the superposition. I don't want to go into that, except that the view I had was if you're trying to join quantum mechanics and gravity together, you can't do this with ordinary quantum mechanics. quantum mechanics has to be modified, maybe modified in a way which this thing we call the collapse of the wave function, which is a very fundamental paradox in ordinary quantum mechanics, how states don't just simply follow the Schrodinger equation, they finally jump when you do what's called making a measurement. Is it gravity that's responsible for that jump? So that is the view. It hasn't really got anywhere with regard to this problem which I've been getting up to. I just thought I'd mention it because it just tells you, and it's where I'd led myself for a long time to say resolve this paradox of why the future and past singularities are different by saying that somehow it's because quantum gravity is a funny theory which involves somehow changing quantum mechanics. I still believe that, but it's not where I want to go for now. Where I want to go for now is another, I don't have much time, I think, but let me just say, it's another way of looking at the singularity problem. This is involving an idea which I'd introduced to try and talk about gravitational radiation. Why not squash infinity down to a finite boundary? And you see in this picture, due to M.C. Escher, it's a wonderful example of how you can represent a geometry where infinity is squashed down into a finite region. You squash it in this conformal way. What does conformal mean? Well, big and small look the same. You can see this in the eyes of these fish creatures. They're circles. The closer you get to the boundary, they still remain circles. The squashing in one direction is the same as squashing in the other direction. Small shapes are unchanged, but sizes are changed. So that's what's called conformal. And it's this trick of conformal, well, it's a trick due to Beltrami in this particular picture, where you can represent this entire geometry. It's called hyperbolic geometry. Don't worry about that. You can squash it down into this finite region, so infinity becomes represented as a finite boundary. Now in space-time, you can do a similar sort of thing. Here we have the light cones. What does the metric do? The light cone is only part of, or the null cone is only part of the metric. It's 9 out of 10 components, roughly speaking. What does the 10th component do? It tells you the scale. What is the scale? Well, it tells you how clocks behave. Well, you see, this combines the two most famous formulae of 20th century physics, Einstein's E equals mc squared and Max Planck's E equals h nu. Put them together, and it tells you that energy and frequency are equivalent. Mass and frequency are equivalent. That's putting the two together. So if you have a massive particle, it knows how the time works. It knows the click of a clock, the tick of a clock. However, a light ray doesn't know the scale. It just travels along the light cone. It never sees these surfaces which represent the ticks of clocks. And so you don't have the scale. So here I have a picture of what you can do when you look at conformal geometry. This is just the Escher picture, if you like, applied now to the universe as a whole. And they've done it to the future by squashing the future down to make this nice finite boundary. You can do this with the cosmological constant, and it forms a nice space-like finite boundary. The Big Bang can be stretched out if it's one of the standard cosmological models, not one of those great messes, as long as it is a nice one like the picture that we have here in the picture there. If it's the standard picture and not the mess that we have here. How do you distinguish the two? Well, this was really my student and then colleague Paul Todd, who suggested a nice way of saying that the Big Bang is nice is to say that you could stretch it out and make it into a nice boundary. So that's really what I've done in this picture here. I stretched out the Big Bang to say it's not one of those horrible messes. It's a nice smooth one by conformally stretching it and formally squashing it. Well, you can do that quite generally when you've got a positive cosmological constant. The nice theorem due to Helmut Friedrich really shows that can be done. So this is the picture. You can squash infinity down, stretch the Big Bang. There's nothing outrageous about this picture. It's just a nice way of looking at, it doesn't tell you why the Big Bang has this nice structure, but it expresses that nice structure in a nice way. This is outrageous. This is the model I put forward about 15 years or so ago, which suggests that, well, it's not just a nice way of representing the Big Bang. The Big Bang was the continuation of the remote future of a previous eon, as I'm calling it. Now you might say, how could anything be more unlike the Big Bang, which is a very hot, dense structure, and the remote future, which is a very, very rarefied and cold structure? Well, you see, once you do the conformal stretching of the Big Bang, it gets colder. When you squash the conformal squashing of remote infinity, it gets hotter. And so maybe it's sensible to match them. It's only sensible to match them if the remote future is nothing but massless particles. It's dominated by photons, but maybe the mass somehow goes away. I have a proposal for that. That's the only most outrageous, perhaps, part of the scheme, is to say that massive particles will eventually lose their mass. It's not so absurd when you look at how particle physics works that this could be the case, but it's an assumption of this scheme that the mass does fade out, and in the remote future you have massless physics. What about the Big Bang? How about the mass there? Well, that happens automatically because when particles get hotter and hotter and they move around faster and faster, the mass becomes more and more irrelevant. That's more or less E equals mc squared. The mass becomes more or less irrelevant and they behave like massless particles. So it's not so outrageous physically. So once you got used to that idea, which most people haven't got used to, you can have this picture that even signals could get across from one side to the other. And I'm trying to say that maybe they do. And there are two ways they might. One is the following way: if you have black holes in the earlier eon, I'm calling it, I call these things eons. This is the previous eon, and this is our eon. This is this picture. This is the previous eon, and this is our one, joining together. Things in the previous eon might be observable in our eon. And here I'm having black holes. Hello? Black holes colliding together, and they produce gravitational waves, and maybe you can see them. And here is some observation picture due to my colleague Vahe Gurzajan, who plots out these. If anybody wants to know, I could explain this picture further, but I think I've run out of time. The idea is that these are the centers of these seeming rings that you see in the sky, and they're very, very non-uniform. So I don't know how you'd explain this anyway other than the CCC picture. That's the conformal factor cosmology picture. The other observational thing is the black hole evaporation. I didn't quite talk about this. We just talked about black holes, but according to the Bekenstein-Hawking idea, you've got the entropy here, and this is associated with the temperature, and then you get the Hawking radiation, where the black holes eventually fade away, and you can see them disappearing. I don't want to talk about this picture too much, but what I do want to talk about is this paper that Christoph Meisner and Pavel Miroski and Daniel Ann and I published in the monthly notice of the Royal Astronomical Society about a year and a half ago, a little bit longer than that, where we see these what we call Hawking points. This horizontal line in the middle of the picture is the crossover from one eon to the next. The lower crossover is what we see. The top line is the last scattering surface. That's where you actually see something. The bottom line is the crossover surface. And here we have a black hole, which is the result of a galactic cluster finally being collapsed into a black hole. That black hole finally evaporates away. All the radiation gets concentrated in this little tiny point. This then bursts into this as you get through, before you get to last scattering, which is 380,000 years to this line here. And what you see is this spot in the sky of raised temperature. And we see these spots in the sky. We see about 6 of them seen in exactly the same places in the WMAP and Planck data, quite different satellites. Their temperatures, spots which are about 8 times the diameter of the full moon, and they're out there, and you see them with a confidence level of 99.98% confidence. So these spots are there, and I don't know of any other theory which produces them apart from the fact that they would be the results of the Hawking evaporation of a black hole in the previous eon. If anybody else has another explanation, I would like to see it. As far as I'm aware, nobody has commented on this paper. I've had people commenting on the previous version, which was on the archive, but that's not the paper that was actually published. And I would like to see comments on where these spots can have come from if they weren't from the explanation that we have here. Thank you very much.
So thank you very much. I can hardly thank you enough for sharing with us your perspective and insight, and also your recent ideas. And we have time for questions, and I really encourage everyone to suggest questions, whether you're faculty or students, everyone. Just please raise your hand so we can try to do it in an orderly manner, and we are able to take questions, right, Roger?
Oh, sure. Yes, thank you.
So let's see, do I see hands raised? I'm not able, oh, here I see, okay. So let's see, Ofek Birenholz, please.
Hi, can you go back, I think, 3 pages to the map of the sky, I presume, and explain what we're seeing in this map? Yeah. What are these points?
I got very rushed at the end. I would like to explain more. Let me say about this. Yes, this is an observation due to my Armenian colleague, Vahe Gerzadan, and he looked for rings. Let me go to the previous picture, because I think that's what I'm trying to explain. Here we have a space-time picture. The plane in the middle is the crossover surface. This is us at the top looking back. And the picture is that we had in the previous eon a collision between 2 supermassive black holes. Now, as they collide, they produce an enormous signal in the form of gravitational waves. Now, the argument is that these gravitational waves will actually get through from the previous eon to ours. We don't see them as gravitational signals. What we see, according to the picture, is how they affect the material that causes the microwave background. So they heat up. Basically what you see, each collision event will produce this cone coming out. Our past cone is another cone. We have to think in this 3-dimensional surface. We have to visualize another dimension here. As these cones intersect, they intersect in a circle. So what you would see looking back is a ring in the sky, which would represent this collision event. Now that ring, according to Vahe's analysis, the ring would be look like a temperature variation which is somewhat lower than the normal variation. So you're looking for a ring of temperature which is slightly less variable as you go around the ring. So that was the test to use. It was an interesting idea. It wasn't what I'd thought of, but it actually was quite interesting. But he didn't look for single rings. He looked for at least 3 rings, which had with the same center. To get a strong enough signal, you had to look for triples of rings. Now, why would you see 3 concentric rings? Well, that's because in the theory, because in this black hole collision, it would happen several times in a single galactic cluster. So you imagine a galactic cluster represented basically a point in the sky. In the next eon, there will be several times this black hole would swallow another one. Bang, 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 at least 3. And you would only see the signals in his examination here when you've got 3 of them at once. So bang, bang, bang. So what we would see would be 3 rings. That's the bottom picture here, which I've deliberately drawn rather faint. 3 rings of lower variance around the ring. And remarkably enough, when he does this, he gets a significant signal. Now, the significance of this was tested because he looked at, I'm talking about this particular picture, which of course I find particularly remarkable, because the centers, these little spots, the blue spots or the red spots, are the centers of triples of low variance rings. Now you see them very crowded. They're not uniform over the sky. So whatever explanation for you have for them, it's very puzzling why they should be crowded. What's more puzzling to me is that the color now comes in. Because what is the color? That is the average temperature. So that's they're not singled out by the color. They're not singled out by the fact that you've got low variance. And what you find is not just that they're clumped in location, but they're clumped in color. Now, what does the color mean? The color is actually the redshift. Now, it's very puzzling because redshift in the color coding actually means cooler. Exactly means warmer, sorry, which is, see, red is actually cooler. And it's the other, don't worry about that. Red actually means more distant for two reasons which cancel each other out. But it means more distant in the theory. Blue means more close. So what you're seeing in this picture is not just that they're clumped in location, in angular location from where we're sitting, but in distance from us. So the fact that they're clumped in color as well as clumped in location is very remarkable. Now, I have not seen anything else which could explain this other than the fact that this is simply a very, very large clump of super duper cluster of galaxies, which are in the bottom region very, very distant, and the top region not so very distant. So these ones would be within our particle horizon, as we call it. The other ones would be outside our particle horizon, which you can do because you can, as you look back into the previous eon, our light cone goes outside what we normally call our particle horizon. I'm sorry that explanation was a bit, I hope it was helpful. But I regard this as a very striking picture because it shows you that there's something non-uniform about the universe, whatever explanation you have. Very non-uniform about the universe, but also it gives something which, where the non-uniformity is explained in the CCC picture, the conformal cyclic cosmology picture that I talked about, and I can't see any other explanation for it. Maybe somebody will come up with another explanation, but these pictures seem to be genuine, and anyway, that's the best I can do with explaining what this picture is. Thank you for the question.
Great. So it's great that we were able to discuss these transparencies. And the next question goes to Shaheen Jabari, please, if you can unmute yourself and answer.
Thank you, Roger, for the very exciting and interesting talk. I have actually two questions. One is about the information problem and the evaporating black hole. And in particular, I would like to know your opinion on the entanglement entropy and how it is relevant to this information problem. And the second question, if I may, is if I got your this picture of the universe that you are showing and discussing just yes, this the one. Does it mean that we are not living in an FRW universe, in an homogeneous anisotropic? Is it? Do I get this correctly?
Let me answer the second question first, because that's easier for me. No, not really. You see, of course, I'm not assuming that it is necessarily a Friedman, Lemaitre, Robertson Walker type model. I think it's probably fairly close to one. This just shows you that it's not as close as people think. There are certain things which one might relate it to. When people look for quasar distributions, they do find quite a lot of non-uniformity. And I was trying to tie it up with this picture because there is a region which they call, what is it, the Great Cluster or something, can't remember. You look for quasars and they are not very uniform. There are big clusters of them. And the biggest cluster which is seen is somewhere quite close to this large blue region at the top. If it had been bang in the middle of it, I would have been very excited. It's sort of on the edge of it, which I can't quite explain. So, but it's interesting. It shows you that there is a connection between the non-uniformity seen in this picture here and something of the non-uniformity if you look very distant, very far enough away, that it's not as uniform as people think. And one way of looking for this non-uniformity is in quasar distribution. So I think that's a nice area to explore, to see how well that ties in with the sort of thing here. It's a bit hard to tie it in with the lower region, with the red region, because that's outside our particle horizon. So you're looking here at a cluster of galaxies, apparently, which you don't see directly from us now. I mean, whatever produced that cluster of galaxies coming through into our eon is not something we could see now, whereas the blue region is. The red region, however, we might see the effects of it. Well, there's a thing called the what's it called? It's called the cold spot. Yes, the cold spot is somewhere close to this. It could have something to do with it. I think there's a lot of scope for looking for, on a very large scale, irregularities, which are not quite Friedman, Robertson, Walker type of picture. So yes, not too far from it, but maybe far enough that would be puzzling to people in the normal sense. Now, as regard to the different kinds of entropy you're talking about, I get very lost with these things. You see, I think people are trying to get around this problem of the black holes. You see, I don't know if I should talk, I didn't really talk about this picture, but this is a conformal. The left-hand part of it is sort of a temporal picture of the black hole finally evaporating away. And on the right-hand side, we have a conformal picture. And you will see that the singularity is really space-like. And so that matter gets lost in it. And so if matter gets lost, then the entropy can get lost. In my picture, some of it does get lost in the singularity, but some of it escapes. And what happens to it? Well, it it gets into the Hawking point. So why you get this, the second law of thermodynamics working in my scheme is that it gets destroyed in the Hawking point. That is, the Hawking point is the picture I had in the last picture, where you have the black hole, the final black hole, which is the swallowing up of a of a supermassive black hole, and all the radiation which comes out of it gets squashed into that point. Now you see, people try to argue that the information comes back or something and talk about these different kinds of entropy and so on. I get lost with all these discussions. So I can't really answer you, mainly because I've never really gone into it. And I think people are trying somehow to get the entropy back out again. I don't know what it is. They're trying to say that somehow the entropy is not lost in the black hole. Some of it gets into the radiation, some of it gets lost in the black hole because it gets onto the singularity, and the singularity is a singularity, and it gets squashed out of existence. So that's the only thing we can say. And in the Hawking point, it gets squashed out of existence, even if it's in the radiation. So the mass comes through, as it comes through into the next eon, as one can show from wonderful theorems, one can prove about the surrounding region where it's not singular. And so the mass must come through, but the information doesn't need to come through. So the argument is that the information is lost there. Whether people try to argue that the information comes back in some way, I just don't follow those arguments. So I'm afraid that's where I get stuck. Best I can do with the other part of your question, I'm afraid.
Thank you. Thank you very much.
Okay, so I suggest that we take a third and last question for the formal part of the talk. And then if Professor Penrose, if you can stay afterwards for additional questions, of course, that as much as you are able and interested. So for the third question, Professor Tzvi Piran, please, if you can unmute yourself and ask.
Hi, good afternoon. I have a question on this repeating universe structure.
Yes.
Do you need inflation in this model? Because I guess that with arranging of this tower of universes, you can probably get rid of most of the problem that inflation is supposed to solve.
Yes, that's an interest. You don't need inflation for this theory. And as you say, the inflation is supposed to solve various problems. One is the uniformity, which it doesn't do, actually, because I can't see why inflation resolves the issue of the complete mess that you get for a generic universe. I just don't see how inflation can do that. There's other issues that inflation is used for, the scale invariance, the close scale invariance of the micro background. You could give an explanation for that in this model without inflation. It's not completely inconsistent with a mild inflation. It's inconsistent with inflation as we understand that theory, which would completely, if you had a crossover between one eon and the next, let's see if I can find one of those pictures. Where are we going? Where was my picture? Sorry, I've gone too far. There we go. Something like this one. You see, when we cross over from one eon into the next, you can't have a big inflation in the normal way it's understood would stretch. There'd be a gap between one eon and the next eon, and that gap would be so big in the conformal picture that no information could get across from one side to the other. It would completely wiped out. So although it's not inconsistent with the picture I presented, it would be inconsistent with any observation that you can make. And since I claim there are observational supports for the model, we can't have inflation which would be at all big. It could have to be something which is quite a small gap between one eon and the next, if you like. It would be like a gap, if you like. There's nothing inconsistent with having a little gap. There is something inconsistent with having a big gap. So the inflation in the form that we currently...
稍等，我还没听完啊，我听完跟你聊。
Sorry.
很快很快。
Yes, I'm sorry. Inflation
很
in
快
the
很快，
form...
你先说，你先。
Sorry?
Someone unmuted by chance. Please continue.
Yes, inflation in the form which inflation is more or less normally accepted is inconsistent with this picture, and therefore inconsistent with the observations of this picture. However, a much more mild inflation, which is only a little gap between one and the next, would be consistent with this picture. So let me leave it at that. There are some interesting new results, which I can't really talk about because they're, I'm working these out with Christoph Meisner, and it's very intriguing, and I can't say any more than that. But all I can say is that a little bit of inflation is consistent with this picture. Inflation, as currently understood, is not consistent with this picture. And not needed, I would say, because the things that it does, I haven't gone through in detail all of the things it's used for, but certainly things like information outside the particle horizon. Sure, you can get that in this model. You'd get something like that in observations. The fact that you have scale invariance, the fact that you can have a spectral index, those things can be explained in this model. I'm not sure I'm aware of all the things inflation is used for, so I can't make a general comment. But as far as I'm aware, pretty well all the things that inflation is felt to be necessary for is explained in this model. Because you see, there is a kind of inflation, namely the exponential expansion of the previous eon. So you have something which looks a bit like inflation from our perspective. So this is us in our eon. We're looking back into the previous eon. We seem to see something like an exponential expansion, but it's not after the Big Bang, it's before the Big Bang. So that's the general tone of what I want to say in response to your question. Thanks for the question. No, they were all good questions, I should say.
Thank you very much. So it was great to see hundreds of people join us today, over 600 people. Many of them, we know each other, so it was so great to see you and so great to see this great talk to the memory of a great Israeli physicist, bringing everyone together. And I encourage you to show your appreciation for this talk by using the applause button on the Zoom, yes. So I hope to see many of these applause here, because if we cannot really clap our hands, it won't sound well. And it was great to see you. Hope to see you in future events. And those of you who are interested to stay for additional discussion, we'll see. Maybe that would be possible, right? Okay, thank you everyone for coming.
Thank you.
Thank you very much.
Thank you.
Thank you very much.
Thank you.
Thank you very much.
Thank you.
Thanks.
Thank you very much.
Thank you. Thank you.
Thank you.